Hello my dear students, today we are going to discuss nuclear chemistry. So before starting with this nuclear chemistry, let's start with the basics of nuclear chemistry. What do you mean by the nuclear chemistry? Nuclear chemistry basically deals with the stability of nucleus and the changes that occurs in the nuclear or nuclear change. This nuclear change has nothing to do with the number of electrons revolving around the nucleus. That means electron has no role to play in this nuclear reaction. What is happening inside the nucleus, that is the nucleons, protons, electrons and neutrons. Protons and neutrons that is present inside the nucleus. The interchange between these two, and within this interchange, what is happening, that is what we call as nuclear chemistry. This nuclear chemistry is not affected by external imposing factors like change in temperature, change in pressure, or the environmental factors. This phenomenon of the emission of the high penetrating or ionizing radiations from the heavy nuclei is known as natural radioactivity, and the nuclei or this heavy element which is undergoing emission is known as radioactive nuclei. So this is basically what is radioactivity, radioactive element or factors affecting this nuclear reaction. Now some basic terms about this nuclear chemistry. Basic terms like isotopes, and we know these isotopes. So let's discuss the definition of these isotopes. Isotopes are those species having same atomic number but different mass number. So when we say the same atomic number, that means number of protons present inside the nucleus is same, but the number of nucleons, that is proton plus neutron, is different. Since the number of proton is same, so these isotopes will have different neutrons. So isotope simply says same atomic number but different mass number. These isotopes have different neutrons. Now since these isotopes have same atomic number, that means their chemical properties are more or less similar but their physical properties are different. The second term that we come across is isobars. Isobars are those species having same mass number but different atomic number. This is just opposite of isotopes. So we have two pair of species whose mass numbers are same but atomic numbers are different. So in this case we have same mass number but different atomic number. So same mass number means number of nucleons present inside the nucleus is same but the number of protons is different. So same number of nucleons but different number of protons. So we have these isobars. Then we have isotones. So isotones means having same number of neutrons. So species, a pair of species having same number of neutrons present inside the nucleus, these are known as isotones. Then we have isodiaphers. Isodiaphers Isodiaphers are basically those species having same isotopic number. So we have a particular term, isotopic number. If the isotopic numbers are same for two different species, then those species are known as isodiaphers. But the question is, what is isotopic number? Isotopic number simply means same number of the difference between neutrons and protons. Those are known as isotopic number. So isodiapher means same isotopic number. So this isotopic number means isotopic number simply defines difference between the number of neutrons and protons. So pair of isomers having same neutron proton difference, these are known as isodiaphers. So we have isodiaphers means having same isotopic number. Isotopic number is difference between number of neutrons and protons. Then we have isosters. Isosters are a pair of species having same number of electrons as well as same number of atoms. Those are known as isosters. Same number of atoms and same number of electrons. So these type of species are known as isosters. As an example, we can take this CO2 and N2O. These are known as isosters having same number of atoms as well as same number of electrons. Then we have nuclear isomers. So I had term nuclear isomers. So nuclear isomers basically means a pair of isomers having same number of protons or same atomic number as well as same mass number but difference in their radioactivity. So those pair of isomers are known as nuclear isomers. So these nuclear isomers having same number of protons and same number of nucleons but different radioactivity will have different decay constant, will have different half-life, etc. And you can also have, we have different nuclear spins, etc. So those are known as nuclear isomers. So nuclear isomers, same atomic number and same mass number but different radioactivity. Those isomers are known as nuclear isomers. So we have some basic terms: isotopes, isobars, isotones, isodiaphers, isosters, nuclear isomers. So we are basically talking about radioactivity, phenomenon of emission of penetrating radiations from the heavier nuclei. So heavier nuclei generally being less stable, this undergoes emission of different types of emission. That process is what we call as radioactivity, and these heavier isotopes undergoes different types of radiation. So different types of emission of different types of radiation. Let's see. So basically we encounter three different types of radiation that is being continuously emitted by these heavier isotopes, and those radiations are we have alpha, simply say alpha rays, then we have beta rays, then we have gamma rays. So basically these are three different types of radiation that is being emitted by heavier nuclei. These alpha rays, these are positively charged helium nucleus. helium nucleus. So helium mass number 4, atomic number. This helium nucleus is defined as alpha rays, beta rays. Beta rays simply means electrons, and this gamma rays are waves, radiation. These alpha rays are positively charged. Beta rays are negatively charged, whereas gamma rays are uncharged. So alpha and beta rays are charged particles, whereas gamma is uncharged particle. Alpha being positively charged helium nucleus, beta is simply nothing but the electrons. Now these radiations shows penetrating power. So when we compare the penetrating power of this alpha, beta, gamma, so means penetrating power means these radiation can penetrate inside a given substance. So we are comparing the penetrating power of these three radiation, alpha, beta, and gamma. Penetrating power increases from alpha to beta, then beta to gamma. So out of these three radiation, gamma rays has got the strongest or the largest, highest penetrating power, whereas alpha rays has got the least penetrating power. These radiations also show ionizing property. That means when these radiations come across some neutral particles, they can undergo ionization. They can ionize those neutral species into ionic species. So that property is known as ionization property. So when we compare the ionization property of these three radiation, alpha rays are found to be the strongest, one that having highest or the strongest ionization property, followed by beta, followed by gamma. So penetrating power and ionizing property both are going in opposite direction. Penetrating power increases from alpha to gamma. Ionizing power decreases from alpha to gamma. These radiations has got different speed. When we compare the speed of alpha particle is approximately 1/10 of speed of light, whereas these beta particles, the speed is from approximately from 30 to 60% of the speed of light, whereas these gamma particles travels with the speed of light. So when we compare the speed of these two radiation, speed increases from alpha to beta, beta to gamma. The maximum speed is gamma, which travels with the speed of light. Slowest particle is alpha. So these are the three radiations that are generally emitted by the heavier nuclei during the radioactive process or radiation process. And these are properties of these radiations. Now after these properties of radiation, so we have properties of different radiations, alpha, beta, gamma. There is a comparison between these properties. After this, we'll move on to nuclear process. Radioactive series. The radioactive series means activity series. Simply activity series. These heavier nuclei undergo different types of series, and let's come into different series. Four series, that is 4 and series. These 4n series, these are also known as thorium series. So why this is not thorium series? Because for this radioactive series, the first element is, or the parent nuclei is thorium. So starting from thorium, this undergoes different types of alpha, beta, gamma addition, giving the final stable daughter nuclei. So why we say this 4n series? Because the parent nuclei and the daughter nuclei, their mass numbers are exactly divisible by 4, and this was in 4 and a maybe any value 1, 2, 3, 4, 5. So these 4n series, this is thorium, atomic number 90, mass number 232. This is parent nuclei. Daughter nuclei is lead, atomic number 82, mass number 208. So starting this parent, this is parent nuclei. This is daughter nuclei. So parent nuclei mass number is 232. So 232 is completely divisible by 4. Similarly, this mass number of the daughter nuclei form lead 208. Again 208 is divisible by 4n. So we say this is 4n series. So doing this, some X alpha particles and some Y beta particles are emitted. So after emission of this alpha X alpha and Y beta particle, this series comes to n, that is formation of the stable nuclei, that is lead. So we say this is thorium series. So thorium series, because starting parent element is thorium. Why this is 4n series? These mass numbers are completely divisible by 4. Second series, 4n plus 1 series. This series is artificial series. This series is also known as Neptunium series. Neptunium series because the starting parent nuclei is Neptunium, that is Np. Why this is 4n plus 1? Because the mass number of the parent nuclei and daughter nuclei when divided by 4, there is a 1 remainder. So this is known as 4n plus 1. (237). So when we divide this 237 by 4, the remainder is 1. And this finally gives the product bismuth, atomic number 83, and this is 209. Again, this 209 when divided by 4, there is a remainder of 1. So this is 4n plus 1, and this also gives some X alpha and Y beta particles. Third, 4n plus 2 series. This 4n plus 2 series, this is also known as uranium series. Uranium series because the starting element is uranium, that is uranium, atomic number 92, mass number 238. So when we divide this mass number 238 by 4, there is a remainder of 2. And this uranium, after a number of successive alpha or beta emission, comes to the stable nuclei, that is lead, atomic number 82, mass number 206, plus some X alpha and Y beta particles. Fourth series, that is 4n plus 3 series. Why this is known as 4n plus 3 series? Because the mass number of the parent nuclei and daughter nuclei when divided by 4, there is a remainder of 3. This series, this is also known as Actinium series. actinum series, because the starting element is, the parent element is actinum. We have this actinum, atomic number 89, mass number 227, and this finally gives lead, atomic number 82, mass number 207. So this mass number 207 and 227, when divided by 4, there is a remainder of 3. So this is known as 4n plus 3 plus some x alpha plus y beta. So these are the 4 activity series that we often encounter in radioactive compounds. So any radioactive compound undergoes emission of this, follow this emission series. So foreign series, also known as fluorine series, foreign plus 1 Neptunium, this is artificial, foreign plus 2 Millennium Series, foreign plus 3 Actinium Series. These are the initial parent compound and the initial parent element and the final element that is formed. So if you look at this, for all these natural series, foreign series, foreign plus 2 series, foreign plus 3 series, the daughter nuclei is lead, Pb, Pb, Pb. Whereas only for this Neptunium series, that is foreign plus 1 series, the final daughter nuclei is bismuth. So when we study the stability of heavier nuclei, the heaviest nuclei that is nuclear stable is bismuth. So bismuth is the heaviest nuclei which is stable in terms of nuclear properties. So elements above this bismuth are unstable and are known as radioactive elements. This is only emitting a number of alpha particles, beta particles as well as gamma particles. So we have this radioactive series. Now during this radioactive series or radioactivity, alpha particles are emitted as well as beta particles are emitted. We have seen the alpha particle is helium nucleus, atomic number 2, mass number 4. So every particular element undergoing alpha decay, there must be change in atomic number as well as mass number. If atomic number as well as mass number changes, that means the daughter nuclear form will have different position in the periodic table. So let's define the position of daughter nuclei after alpha, beta and gamma decay. That is what we call as group displacement law or group displacement theory. Group displacement law. That means these radioactive elements undergoing radioactive emission, alpha beta gamma emission, after alpha beta gamma emission, there is change in the position of the daughter nuclear form. So the change in position is nothing but change in the group number in the periodic table. So we will find out. So first take up this alpha decay. So we have alpha particle. Alpha particle is nothing but the helium nuclei. So a particular substance or a particular radioactive substance undergoes this alpha decay. For every alpha decay, there is decrease in atomic number by 2 unit and mass number by 4 unit. If the atomic number decreases by 2 unit, then the daughter nuclei formed will be placed two place on the left side of the parent nuclei. So look at this. Atomic number decreased by 2 unit, atomic mass decreased by 4 unit. So the daughter nuclei that is formed after this alpha decay will be 2 placed on So 2 plane means 2 groups on the left of parent nuclei. So look at this. Suppose this is period. So we have, look at this. Suppose we have element X. Let's assume this element X is undergoing radioactive decay. This atomic number is A. Suppose this mass number is P. Now this undergoes alpha decay. After this alpha decay, there is decrease in atomic number by 2 units. So look at this particular group, -1, -2. So suppose the daughter nuclei form is Y. That means we have this X, A, P changes to Y. That is P -4, A -2 plus alpha. So this is A -2, this is P -4. So this is parent nuclei, this is daughter nuclei. So after alpha decay, the daughter nuclei form is placed 2 groups behind this, the parent nuclei. So this is the position of the daughter nuclei formed after alpha decay. So basically the point is atomic number decreased by 2 units. So this will replace 2 units on the left side of this parent nuclei. So this is what we call as group displacement law, changing the position of the group. Second, suppose this beta decay. We have this beta decay. Now beta is nothing but electron. So electron we have -1 charge, mass is approximately 0. So alpha decay, suppose we have looked at this. During this alpha decay, mass number remains constant. So there is no change in the mass number of the daughter nuclei from the parent nuclei, whereas atomic number increased by 1 unit. So if the atomic number increased by 1 unit, that means the daughter nuclei formed will be placed 1 group ahead of the parent nuclei. That means 1 group on the right side of the parent nuclei form. So suppose we have this X, atomic number A, mass number P. This changes to a daughter nuclei Y. So increase in atomic number by 1 unit. That means atomic number should be A plus 1. Mass number remaining same. So this is parent nuclei, this is daughter nuclei. So in terms of this position in periodic table, this is period. Suppose we have this is parent nuclei A, mass number P. This undergoes beta decay. After beta decay, there is increase in atomic number by 1 unit. So this is the parent changes into daughter nuclei. Atomic number increases by 1 unit. Mass number remaining same. So this is 1 group on the right side of the parent nuclei. This is parent nuclei. This is daughter nuclei. Alpha. Whereas in case of alpha decay, the daughter nuclei is placed 2 groups behind the parent nuclei. So this is beta decay, this is alpha decay. Then we have third decay, that is gamma decay process. Now gamma particles are uncharged. After this alpha decay and the beta decay, the daughter nuclei is in nuclear excited state. These daughter nuclei formed after alpha and beta decay being an excited state. To come back to its normal ground state, some energies are released and that energy falls in gamma. So gamma decay is nothing but the energy rearrangement after alpha and beta decay. So during this gamma decay, there is no change in the position of the element. So this is simply energy rearrangement. So I told you, after alpha decay and beta decay, the daughter nuclei formed is in excited state. So those daughter nuclei being in excited state will try to come down to the normal ground state. So during this process, energy is released and that energy goes in gamma particle. So this is simply energy rearrangement. So there is no change in position. No change in position in the periodic table. So gamma decay, there is no change in position. Beta decay, the atomic number increased by 1 unit, 1 cube on the right side of the parent nuclei. Alpha decay, the atomic number decreases as 2 units, and the other nuclei is placed 2 groups behind this parent nuclei. Now, one thing to be remembered, which is an important one, which you have to keep in mind is this alpha decay and beta decay. So there is change in the group according to this group displacement law. This group displacement law is not applicable to lanthanides and actinides. Law is not applicable to lanthanides and actinides. Why? Because these lanthanides and actinides, these are always placed in third group. So these lanthanides, even after going under alpha decay or beta decay, the parent nuclear form will also be placed in third group. So normal alpha decay, beta decay, normal group displacement law is applicable, but in case of lanthanides and actinides, this group displacement law is not applicable. Why? Because these are placed in third group, except the first elements like lanthanum, actinum, lawrencium, and lutetium. Except these 4 elements, this is the last element of lanthanum actinide series. This is the first element of lanthanum actinide series. So these first 2 elements and the last 2 elements, except these 2, this group displacement law is not applicable for lanthanides and actinides. So this is alpha gamma decay. After this, we also have some other types of decay process, that is beta plus, which is also known as positron. Positron decay. Positron decay. So positron is nothing but a positively charged electron, that is anti-electron. So positron electron with one positive charge, this is positron decay. So let's see what is positron decay. During this positron decay, atomic number decreases by 1 unit, but mass number remains same. So look at this, atomic number decreases by 1 unit. If atomic number decreases by 1 unit, so the daughter nuclei formed after this positron decay will have 1 unit atomic number less than the parent nuclei. So the daughter nuclei formed will be placed 1 group behind the parent nuclei. So suppose look at this. This is period. Suppose we have this parent nuclei. Now this undergoes positron decay. atomic number decreases by 1 unit, so the total nuclei formed will be A minus 1, mass number remaining 10. So the position decreases by 1 unit. So this is beta plus decay. This is parent, this is daughter nuclei. So a positron decay means decrease in atomic number by 1 unit. So this is group displacement law for positron decay. Apart from this, we also encounter another type of decay that is known as K capture. So this K capture is nothing but K stands for K shell, that is kernel. Sometimes the heavier nuclei absorbs an electron from the K shell. So when this nuclei absorbs electron from the K shell, there is a deficiency of one electron in the K shell. So this electron that is being captured by the nuclei, when there is one electron less in the K shell, so to overcome this, some electron from higher excited level fills the vacuum created by this electron captured by nucleus. So electron is coming from higher level to the lower level. So during this process, look at this. Electron is remaining inside the system. Nucleons, number of nucleons, protons, nuclei, and as well as neutrons remaining inside the nucleus. So there is no change in the number of protons as well as the number of neutrons. So T capture, simply also known as electron capture by nucleus from a shell. So there is no change in position. No change in position. So notice when electron is coming from higher excited level to the lower level, energy is released and this energy falls in X-ray. So characteristics, X-rays are released. So during K capture, electron is captured by nucleus from the K shell. So to fill this vacuum, electrons are coming from excited level. During this process, energy is released which falls in characteristic X-ray. And since the number of nucleons inside the nucleus remains unchanged, so there is no change in position. So this is different types of decay and change in position of the groups. So we have this group displacement law. After this group displacement law, we are often seeing these electron radioactive substance undergoing emission of alpha, beta, gamma, and the question is, during this decay process, how many alpha particles are emitted and how many beta particles are emitted. So that is calculation of number of alpha particles and beta particles. Calculation of number of alpha and beta particles. That means during radioactive decay process, how many alpha particles and beta particles are emitted. Suppose, let's start with this. We have a parent nuclei with atomic number A. Suppose this is mass number P. Now this changes to daughter nuclei Y. Atomic number is D and mass number, suppose this is Q, plus some X number of alpha particles and Y number of beta particles. So we have to find the value of X and Y. For X is number of alpha particles, Y is number of beta particles. Number of alpha particles, which is nothing but X. So for every alpha decay, there is decrease in mass number by 4 units. So we'll take the help of mass number. So number of alpha particle S is equals to mass number of parent nuclei, that is P, minus mass number of daughter nuclei, that is Q, divided by 4. Why 4? Because each alpha particle mass number changes by 4 units. So difference in mass number of parent nuclei and daughter nuclei divided by 4, this gives you a quantity which is known as H, that is nothing but the number of alpha particles. Next is number of beta particles. Number of beta particles. That is, you have to find the value of Y. Now, during this beta decay, there is no change in the mass number, so we cannot take care of mass number change. But during this beta decay, atomic number changes by 1 unit, so we'll take care of atomic number. So, during this decay, atomic number on left hand side and sum of atomic numbers on the right hand side must be same. So, equating atomic numbers on both sides, we have looked at it. A and must be equals to B plus. Now for every alpha particle, atomic number decay changes by 2 units. So we have 2 times X, and for every beta particle, atomic number changes by 1 unit. So beta particles are negatively charged. So we say this is Y times minus 1. So this value must be same. Why this is minus 1? Because betas are negatively charged, alphas are positively charged. So therefore, Y, that is number of beta particles, this is equals to B plus Y is X minus A. This gives you the number of beta particles and this gives you number of alpha particles. Now we'll find some examples to calculate number of alpha particles and number of beta particles. Let's take some examples. Now just before this we have discussed some series. Now let's try to find number of alpha particles and beta particles and different series of radioactivity. Let's see foreign series. That is thorium series. We have this thorium atomic number 9232 giving you lead 208 82 plus X alpha plus Y beta. So let's find the number of alpha particles. This is the value of P, this is the value of Q. So we have 232 minus 208 divided by 4. So we have 24 divided by 4, so this is 6. So this foreign series or thorium series, moving from thorium to lead, number of alpha particles emitted is 6. Now let's find the number of beta particles. So we have B plus twice S minus A. B is, this is 82 plus 2 times alpha, X is 6, so 2 into 6, twice X minus A is 90. So we have to look at this 82 plus 12 minus 90. So 82 plus 12, 94. 94 minus 90. So we have 4 beta particles. So foreign series, number of alpha particle is 6, number of beta particle is 4. Secondly, for n plus 1 series, Neptunium series, we are looking at this Neptunium 93, 237, Bismuth 83, 209 plus X alpha plus Y beta. So therefore, X, number of alpha particle is 237 minus 209 divided by 4. So this comes out to be 28 divided by 4. 7 alpha particles and y number of beta particles. So we have 83 plus 2 into 7 minus 93. So 83 plus 14 minus 93. So we have 97 minus 93. So this comes out to be 4. So Neptunium series, alpha particle is 7, beta particle is 4. Then we have 4n plus 2, that is uranium series. We have uranium 92, 238 changing into lead 82, 206 plus x alpha plus y beta. So alpha, that is x, is equals to 238 minus 206 divided by 4. So this is 28. Thirty-two by 4. So this is 8. Number of beta particles. So we have 82 plus 2 into 8 minus 92. So 82 plus 16, 98 minus 92. So we have 6 beta particles. Then the fourth series, 4n plus 3 series, we have Platinum series, AC 89, 227, changing into lead 207, 82 plus x alpha plus y beta. So therefore number of alpha particle is 227 minus 207 divided by 4. So this is 20. So 20 by 4, 5 beta particles. Number of alpha particles 82 plus 2 into 5 minus 89. So 82 plus 10, 92 minus 89. So we have 3. So this is how we define number of alpha particles, beta particles during radioactive decay. So this is calculation of number of alpha particles, beta particles. Now, once we know how to calculate number of alpha particles and beta particles, then we have to see the rate of decay. The rate of decay of radioactive substance. The rate of decay or disintegration. Now all the radioactive decay process or disintegration process, this decay or disintegration process of radioactive substance all follows first order kinetics. Now since radioactive decay follows first order kinetics, that means all first order kinetics characteristics will be equally applicable to radioactive decay or disintegration process. So coming to first order kinetics, let's have a quick recap of first order kinetics. Suppose we have the substance A, which is a radioactive substance. This is undergoing decay to give you the final product B, that is the stable nuclei. The number of initials, suppose starting with NO atoms of radioactive substance. after time t, after certain time t, number of radioactive atoms of A left is Nt. What is number of radioactive atoms? Now look at this. Normally in first order kinetics we take the help of either pressure or concentration. Now radioactive substance we don't express in terms of concentration or in terms of pressure. So this radioactive substance is defined in terms of number of radioactive atoms. So number of radioactive atoms initially is NO. After this number of radioactive elements left after time t, that is Nt. Then according to first law, rate of decay. So this rate is equal to minus dN divided by dt, change in number of radioactive atoms divided by change in time. So this is equal to lambda, and what is lambda is known as decay constant, which is nothing but rate constant k. Decay constant, nothing but this is k. So just to differentiate from normal first order kinetics, we use this lambda to define this radioactive decay constant. So this is decay constant, this is number of active nuclei, change in active nuclei divided by change in time, that is the rate. So this is differential rate law. So differential rate law, that is first order kinetics. Now on integration will get ln NO by NT is equals to lambda T, that is integrated with the equation of first order kinetics. This can also be written as log NO by NT is equals to lambda T divided by 2.30 T, that is logarithmic base 10, logarithmic base E. The same expression can also be written as NO by NT is equals to exponential lambda T, or we can also say NT by NO is equals to exponential minus lambda T. That means number of atoms left after time t, that is Nt, is equals to N naught, initial number of atoms, exponential minus lambda T. So simply saying, these are all equations that is applicable to first order kinetics. So all the characteristics of first order kinetics will also be equally applicable to the radioactive decay process. Now some important characteristics of this first order kinetics, that is half-life, so half-life means time required for this initial amount to be decomposed to the half of the initial value. This time is what we call as half-life. Now since this is the first order kinetics, so the half-life of this radioactive substance is equal to 0.693 divided by lambda, decay constant. So half-life of a radioactive substance is independent of initial number of radioactive atoms present. And we have average life, that is T average. So by definition, this T average is defined as 1 by lambda. So we have this 1 by lambda is defined as average life. So this is, so we have this relation half-life and lambda, so therefore lambda is 1 by lambda is 0.693 divided by half-life. So we have 0.693 divided by half-life. So therefore we can say this T average is equals to half-life divided by 0.69 sorry, let me make this correction. We have this half-life is 0.693 by lambda. So 1 by lambda is half-life into 0.693. So therefore, look at this. We can replace this lambda in terms of half-life. So we have 1 by lambda is T half-life. So look at this. T half is equal to 0.693 by lambda. Or therefore, look at this. 1 by lambda is equal to T half by 0.693. So therefore, look at this. T average is equal to 1 by lambda. So 1 by lambda is equal to half-life by 0.693. So this is T half-life by 0.693. Or we can say simply this is 1.44 times is half-life. So this is the relationship between average life and half-life of a radioactive substance. Now look at this. We have this relation Nt is equals to n naught exponential minus lambda t. So A t equals to T average. Nt is equals to n naught exponential minus lambda into 1 by lambda. So that is n naught exponential minus 1, that is n naught by E. So therefore look at it, this Nt, that is n naught by 2.73, that is 36.7 times n naught. That means during this average life, the quantity of radioactive substance left is 36.7 times its initial value. That is the quantity of substance left. So therefore look at this. The radioactive substance decay during average life. So amount left is 36.7% of initial value. So active substance decay is 100 minus 36.7. So this is 3. So approximately 63.3% is decayed. So simply look at this. By looking at this equation, we can also simply say the average life is the life during which 63.3% of the radioactive substance is decayed. Okay. Or simply you can see average life is 1 by decay constant. Then look at this. Amount of radioactive substance left after time, after a number of half-lives. So suppose look at this amount Nt, that is n naught by 2 to the power n. N is number of half-lives. So after n number of half-lives, the quantity of radioactive substance left is n naught by 2 to the power n. And total time t is equals to n into half-life. N is number of half-life multiplied by half-life. This gives the total time. This is amount left after n number of half-lives. This is total time during which we have n number of half-lives. So n number of half-life into half-life gives you the total time. Resident fraction of atom decayed. How much of this atom is decayed? So fraction of atom decayed is n naught minus Nt by m naught initial minus amount that is amount reacted divided by initial amount, that is known as fraction of the atom decay. This is equal to 1 minus nt by n naught. Now we have this nt by n naught from first order kinetics. So 1 minus exponential minus, this is the fraction of the atoms decay during a particular time t. So this is total time nt left after half-life. So these are the various equations that is applicable to first order kinetics. Now sometimes this radioactivity is also defined in terms of activity. We come across certain terms like activity. So simply saying activity is the rate of disintegration. Rate of disintegration or decay. So rate of decay or disintegration, that is defined as activity. Now look at this, we have this first order kinetics minus dn by dt, that is the rate of disintegration. So rate of disintegration, this is defined as activity, and this is equal to lambda n. So lambda into n, that is decay constant into active nuclei, that is equal to a. Now we have integrated that equation, that is nt is equals to n naught exponential minus lambda t. Now multiplying both sides of this equation by lambda, so we have lambda nt is equals to lambda n naught exponential minus lambda t. So lambda is defined as activity, so activity of the substance after time t is equals to initial activity exponential minus lambda t. So in many of the cases, rather than using number of active nuclei, we also use in terms of activities. Activity simply means rate of disintegration. That is A, which is defined as minus dn by dt, or this is lambda into n. Now we'll define this n into mass, the rate of disintegration and mass. So we have this equation minus dn by dt is equals to lambda n. Now we have to replace this atoms in terms of mass of the active substance. So look at this, we have number of moles, this is defined as number of atoms divided by the Avogadro number. This is also defined as mass of the given substance divided by molecular mass of the substance. So we can replace, therefore look at this, number of atoms is equal to mass of the given substance into Avogadro number divided by molecular mass. So sometimes we can also define this in terms of mass of the active nuclei. So therefore this minus dn by dt is equals to lambda n is equals to w na divided by molecular mass. So this is in terms of mass of radioactive substance. So we are getting a term here, activity. So unit of activity. We have different units of activity. So standard unit is becquerel. BQ. So this is SI unit. So 1 becquerel is equals to 1 disintegration per second. So this means disintegration per second. So 1 disintegration per second is known as 1 becquerel. This is standard unit. We also have different unit, that is QD, CI. So 1 QD is defined as 3.7 into 10 to the power 10 disintegration per second. So therefore look at this. This is equal to 3.7 into 10 to the power 10 becquerel So we have becquerel unit, we have Curie unit. So basically we use these two units to define activity. So out of these two units, this is the standard unit, that is SI unit. So 1 becquerel, 1 disintegration per second. So this is activity. So this is unit of activity. So all the characteristics of first order kinetics is equally applicable to this radioactive decay process. Now once we have this radioactive decay process, one of the most important application of this radioactive decay process, carbon-14 dating. And this application, now this carbon-14 dating is used for determining life of wooden artifacts and wooden substance. Now what is happening is, in the upper atmosphere we have a cosmic radiation. Now this cosmic radiation, now on striking the nitrogen nuclei, this is converted into a heavier isotope, that is radioactive isotope of carbon. So nitrogen present in the atmosphere, on reaction with this cosmic rays, this nitrogen is converted into radioactive carbon, that is carbon 14. Now this carbon 14, that is radioactive, combines with oxygen present in the atmosphere, and this is converted into carbon dioxide. And this carbon dioxide is taken by plants during the process of photosynthesis, converting into carbohydrates, and these carbohydrates are taken up by animals. So we have a cycle. During this cycle, this radioactive carbon is ultimately present in the plants and animals. Now as long as the plants or animal is alive, there is continuous consumption of this radioactive carbon, that is carbon 14. When the plant dies, there is no more consumption of carbon 14. So the carbon 14 being radioactive, this radioactive isotope carbon 14 undergoes decay process. Now from the decay process, we define what is the lifespan or the life of that wooden artifact. So this is one of the very good method for defining the the lifespan of any wooden substance. So this is basically used for wooden substance. Apart from this, we have a number of application of this radioactive substance. Now radioactive substance is used for defining the mechanism of chemical reaction, that is known as isotopic leveling. So during isotopic leveling, we have isotopes, it means radioactive isotopes are used, and this part is measured, that is mechanism of reaction. Now we define these radioactive isotopes in medical science. So for treatment of various types of ailments, we use radioactive substance. For defining the life of any particular substance, like life of Earth, we define life of Earth, that is basically some billions and billions of years. So to define this, we again use a concentration of the atomic nuclei of uranium and pitch black. So from this, we can define the lifespan of any given unknown substance. So these are some of the applications of nuclear chemistry. So in a nutshell, we say, though we are saying that this is a chemistry, but this chemistry is unaffected by external imposing conditions like temperature, pressure, and environmental factors. Nuclear chemistry basically deals with nuclei, stability of nuclei, and how these nuclear changes taking place, that is conversion from neutron to proton, proton to neutron, and different types of process that is taking place inside this nuclei. And when we have an unstable nuclei, that unstable nuclei immediately emitted a number of radiations like alpha, beta, gamma, and that is what we call as radioactivity. So this is a brief of nuclear chemistry. Thank you all.